When alcohols are protonated by an acid, they're converted into good leaving groups. And we've seen before that when the acid has a nucleophilic counterion like HCl, HI, and HBr, we're going to enhance substitution. However, in this video, we're going to talk about when a non-nucleophilic counterion pairs up with that acid, we're going to actually enhance the elimination pathway instead. So let's have a look. We can do this for primary alcohols via an EN2 type, or excuse me, an E2 type mechanism. We can do this with secondary alcohols, sulfuric acid and heat. Treat those, and we'll proceed via a probably E2 but arguably E1 mechanism. It's still a little bit debated out there. We distrust the secondary cation though. And then tertiary alcohols will undergo E1 most assuredly. And so again, the reagents are just sulfuric acid, perhaps in a solvent of water in reflux conditions. And we'll get the most stable product because we've got equilibrium type conditions. And so due to sequential reactions, we can actually have the pi bond that we get in the first elimination move around until it finds the most stable position for that alkene. So we're going to get a Zaitsev product even if the bond has to move a little bit. So let's look at an example that will illustrate this to us. A lot of energy in this system and a lot of heat that can help us get over those barriers, and the catalyst acids in there as well. So let's take a look at this first reaction that I've got here. And so if we were going to do this via as a line reaction, this is our prep. We'd have a reactant alcohol reacting with sulfuric acid and heat to give us the alkene that we see, but the double bond ends up in a kind of an odd place. So let's look and see how that happens by looking at the mechanism of this reaction. So first things first, sulfuric acid is a strong acid if there is a solvent of water, and a lot of times there is, so you're not dealing with fuming sulfuric. It's going to have already transferred its proton to H3O+, so that's what I'm invoking here to accept or to donate our proton. So it's a Bronsted acid. So we're going to protonate our alcohol. Now we've got a good leaving group. Well, in the presence of more of that solvent, we can pull the beta hydrogen anti-periplanar fashion to do an E2 elimination. We've got a good leaving group, a very poor base, so this takes a while. It's very slow. A big delta plus has to form on that carbon before it gets started, but it will go eventually given enough of a push. Then we form an alkene that we see here. But if we remember back to our alkene reactions, alkenes can actually react with sulfuric acid, H3O+ here, to form a tertiary Markovnikov cation for this particular alkene. And so then we undergo that reaction, a sequential reaction, after our E2. We initially had E2, but we have to look and see if we can get to a better place with our alkene. And if we can get more stable than a di-substituted exocyclic double bond, we have to. And so we go to via a reaction here, similar to E1, we would see the formation of a more stable tri-substituted alkene where we have our thermodynamic well. It's the most stable form because it has a lower energy than the other alkene. In our potential energy diagram, it's going to have a more favorable equilibrium constant because of that lower energy. So we're going to settle on a major product that we have in the square there. If we have a secondary alcohol, we may have to check for that kind of bond migration. Not for this one though. We're just going to protonate. And let's take a look at the traditional view. We're going to have an E1 elimination to form the hotly contested secondary carbocation. And if we do that without a good nucleophile present, our poor base, the solvent, can come in, grab that proton, and form a major product of the Zaitsev product, the trans isomer here. It's more stable due to the groups not interfering with each other due to torsional strain. Even if we had formed a Z isomer, it would just react again in equilibrium conditions, and at a certain equilibrium constant settle on a major product for the trans isomer. You'd get a little bit of this Z product, but it's going to be a minor product in these conditions. Now, the latest view on this secondary is that we're not going to go through that secondary carbocation. We are going to still protonate to activate our leaving group, but we're going to undergo E2 elimination instead. So yes, that leaving group, it's really going, before it leaves, it's going to be all the way out here. Okay, it's going to be way, way long. There's a big delta plus forming on that carbon. If I can get that out there. Yeah, it's definitely approaching a carbocation, but the carbocation's so unstable, most chemists don't believe it's there, and there's data to support it. The data for E2 elimination is not as convincing as substitution data, but it is out there. Either way you decide to do it is fine on the exam. Either one of these views that we see here, the SN1 path or the E1 path or the E2 path, will work. They both give us the same answer. They give us a Zaitsev product in all cases. Even if we had it stereochemically locked into the E2 elimination in a non-Zaitsev, it would just react again, form a planar carbocation, and then proceed through E1. But that initial step is likely E2, and then if it gets followed up by a carbocation reaction, that's going to be part of the process eventually, but just not initially. So we are kind of splitting hairs there. All right, if we have a tertiary alcohol, there's not much of a debate here. We're going through an E1 type mechanism by most accounts of the data. And so we see we get a proton transfer, we get our good leaving group. The tertiary cation is stable enough to form in a reasonable amount of time in these conditions with all the blasting of the heat. And then we form the more substituted double bond again, our weak base solvent, our ionizing solvent. If we have a strong base, we can't go through this path. We can't have a strong base in the presence of a strong acid anyway, but the E1 path will complete to form our most stable product. We'll draw it down here. How about, there we go. Okay, so we would end up with the more substituted alkene. Again, there's no stereochemistry here because of the equal methyl groups. If there were, the Zaitsev product would form. Now, a few quick notes. The reaction rates are just like substitution. Tertiary is faster than secondary, is faster than primary because of those positive charges building up. We don't like those to build up, so and then they take longer because of that. Consequences of the equilibrium conditions are going to be that the pi bond can move around a little bit because of sequential reactions like we saw in the primary alcohol example. Ring expansions and rearrangements are also possible, even with secondary systems, if they proceed via the old E1 path or the newer consideration, the E2 path. Let's look at one that does both of these things, a sequential reaction and a rearrangement, as quickly as we can. So we're going to protonate again via the same pathway, but look at what product we get. Very different than what we'd expect. So if we look at this, the old SN1 or E1 path here would eliminate this leaving group, giving us a secondary unstable carbocation that the ring would then open up to and form, if we count our carbons and keep track of everything, starting with the cation, 1, 2, 3, 4, and 5 around the ring, we're going to get a 5-membered ring, keeping track of everything here. At position 1, at position 1, 2, 3, 4, 5, we have a methyl group, there it is. The cation forms at position 3, 1, 2, 3, because that's where the bond left from, is that position. Even if you'd drawn it down here, it would still leave from the more substituted carbon on that ring. And then, always trying to get back closer to our groups, we would have a solvent molecule complete the E1 mechanism and form an alkene here. But it's not done. It's going to undergo an additional reaction because we're hot and we've got plenty of time here and a catalyst at work. And so now we can imagine getting closer to a more substituted double bond by reacting at this position, putting the hydrogen on the left and the plus charge on the right. And then we can get another E1 to give us our more stable alkene and the final product. The highest percentage product of this equilibrium system, the most stable alkene possible for this arrangement of carbons. Now, if we were going by the old or the new way of thinking, we would avoid the secondary carbocation initially, this one, and invoke instead neighboring group assistance. So we would do everything in one step. As this bond gets longer and starts to polarize, this cyclopropane will nudge around, get close enough, and then assist the leaving group leaving. And what it does is it gets us straight to this intermediate without going through the secondary carbocation initially. There's enough energy pent up in this cyclopropane to generate the final secondary carbocation, but it avoids that spontaneous production of a secondary cation. So either way you prefer, both will work.